Welcome to Lab 2 for Physics 2. So the goals for this lab is it's a continuation of Lab 1 with tapes and charges, but for this one, the charge is not concentrated on one point on the tape, and it's no longer a point charge. Instead, it's uniformly distributed across the tape, and we also had to make a computational model for this. Some key concepts. So here we're using Newton's second law, which is equal to F net is equal to the change in momentum over the change in time. We also sort of use the velocity update formula, which relates velocity and net force. And we also had to use gravity, so the force of gravity is equal to negative mass times g in the y direction. M is the mass of the object. G is the acceleration due to gravity pointing in the negative y direction. G, we used 9.81 meters per second squared. We also had to use the electric field of a rod, or uniformly distributed charge, and we treat the tape as a rod because of the uniform charge density. The observation point is perpendicular to the charged tape and on the center line, so then the electric field considers the separation distance between observation point and length of tape. So our equation is E rod is equal to K times Q over r times the square root of r squared plus L over 2 squared, where r is perpendicular from the center. We use this equation to estimate charge on tapes. For Coulomb's law, the r vector points from source to observation point. The equation is k times both charges over r squared times r hat, and then we set the point charge at observation point and net electric external field equal to each other to the force. So then some assumptions made were the evenly distributed charge across the whole tape so that we can model the U-tapes as multiple point charges. There's no air resistance, and there's equal charge across both of the tapes. So here's the data and calculations. Some of these are from Lab 1 when we actually did the experiment. So the length of the tape, 0.18 meters. The width of the tape, 0.019 meters. Surface area was 0.00342 meters squared, which is just the length and the width multiplied together. The number of atoms we got from the equation surface area divided by the area of the atom, we got 3.42 times 10 to the 17 atoms. And we measured that the vertical distance between the tapes was 0.025 meters. And then the weight of the tape, we multiplied the length of the tape times the density of a tape and multiplied that times g to get 0.001764 newtons. Some calculations we used the equation for the electric field of uniformly charged rods so that we can estimate the charge of the tapes. Then we set the magnitude of the electric force equation to equal to the magnitude of gravitational force on the tape. And so we got our Q value of 2.14 times E times 10 to the 8th, and we used this value to estimate the charge of the tapes. Now onto the code. So we have our constants here, our mass, which we calculated, and our Q, which we calculated, and the measured distance apart. And here's our function from Lab 0. We've already been through this. And so we're adding up now all the individual electric forces. So for the top tape, we're doing the arrow. The position is the charge at the top, and the axis is our scale times the electric field at the top. Then for the bottom, we iterate through each piece of charge on the bottom tape, calculating the electric field, and then from that, calculating the electric force. And then, as you see, we're doing the on top is equal to the force on the top plus the force of the charge on the top by the bottom. And then we're creating the arrow for the net electric field. Now for the arrows, we're using our scale and calculating the electric force on the top tape due to the bottom tape, but this is just making our arrows, editing the axis to create the arrows for both the electric force vector and the electric field vector. And here is a look at our computational model. My code is also linked in the abstract. So we see that the charge of tapes is 2.3914 times 10 to the negative 8 coulombs. The deficient electrons is 1.495 times e to the 11 electrons. So in order for the U-tape to float, the net force must equal to 0, so the gravitational force is equal to the magnitude of the electric force from the U-tape. Potential sources of error are not completely and perfectly accurate length and width of the tape, not completely accurate distance apart, and the U-tapes might not have been parallel, and there might have been some rounding errors. So what if? What if we see that question, and I said that the point charge model for Lab 1 is equal to 1.11 times 10 to the negative 8 coulombs. Line charge is 2.4 times 10 to the negative 8 coulombs. The line charge has a greater charge, about a factor of 2.15. And why? Why do these estimates differ? Difference is due to the singular port charge compared to the uniformly distributed across rod-like situation, and the line charge is really closer to the real value.